So this is our second lecture here. And yesterday we talked a bit about Knaser's theorem, the basics of sum sets. This time we're going to be talking about Kemperman's critical pair theory. So again, we have our abelian group, G. We have a pair of finite and empty subsets, say with stabilizer H. And then Knaser's theorem tells us, well, let's suppose that we have this bound here that we're no more than the sum of the cardinalized minus 1. That was kind of this threshold bound that we saw. For in the torsion-free case, we're always at least this bound. And if we're in the torsion case, or somewhere there, and we're strictly less than this bound, we have this periodic behavior that happens. And so right at a plus b minus 1, we have like a bit of a transition going on. Knaser's theorem means we actually have equality. And why is this the case? We know it's always at least this much over here. Knaser's theorem says it's at least this much over here. If it was strictly more, we just have this. We would multiply both sides by h. Right? This becomes a plus b. This becomes at least a, this becomes at least b, and we'd be strictly more than this bound over here. Right? So we can't have that. The equality has to actually hold with equality over there. So if we're interested in characterizing all the subsets that are of small cardinality, say below this bound, when we mod out by Knaser's theorem, these are an aperiodic sum set. It has at least this bound. If it was one more, we'd be actually above this threshold by multiplying by h, and therefore we're exactly equal to this bound here. And so this question over here, at most a plus b minus 1 for the cardinality of a bound reduces to the case when equality holds for aperiodic subsets. All right, so these are at this very threshold bound over there. But if we can characterize all possible sum sets that satisfy this equality, the sum set has size a plus b minus 1, and it's aperiodic, then via Knaser's theorem, we'll have characterized all of them. What exactly do these sets look like? Knaser's theorem is giving us an approximate result. If we're strictly below this bound, it's saying the sets would have to be periodic, but it doesn't tell us what happens right at the threshold. So Kemperman's theorem, which we're going to talk about today, is the one that actually gives a full characterization of all possible sum sets satisfying a plus b minus 1 for the upper bound. And so it's kind of rare because it's valid in any abelian group. It's a precise if and only if characterization. I mean, there are lots of approximation results that say if you're above a certain threshold, small sum set, that it must be approximated by some other nice structure. But there aren't so many that are precise enough that they're if and only if statements, and even less so in an arbitrary abelian group. Let's kind of take a look at what kind of sets could satisfy this bound over here. So we're going to think about these as sort of critical pairs. Hence the name critical pair theory. They're the ones that sort of attain this threshold. We want to characterize what they look like. So how can we attain that bound? And there are various ways we could do this if we thought about it. Well, one simple way All right, so what if one of the sets of size is just 1? All right, that's pretty simple there because then we're just translating the sets. I'd say A has size 1. And this is just the cardinality of B, which is A plus B minus 1. So that would be one way of getting equality. If one set has very small cardinality, just size 1, we're just translating the sets and the equality holds. All right, not terribly interesting because it's a very degenerate case, it seems. Maybe a more robust case. What if, yes? All right. So let's try and find a more robust case. This one is the one that kind of comes from the torsion-free case. What if A and B are both arithmetic progressions? And say have common difference. And we'll assume that A plus B minus 1 is no more than the order of D, because this is, of course, a finite element, non-zero element inside G. If you add two arithmetic progressions together, it's not so hard to check. For instance, if you have something that's 0, D, 2D up to A minus 1D, and you add it to 0, D, 2D up to B minus 1D. Well, in the end, what you're going to get is 0, D up to A plus B minus 2D. And as long as we have this condition over here, these are all distinct elements, and you have exactly that bound over there. So it will be another case when you get equality. Now, I know we don't have to characterize the periodic case, but we can look at this example over here. A third example. Let's say A and B are both contained inside H, a finite subgroup. And suppose A plus B equals exactly H plus 1. All right, remember from the last lecture, if we have at least H plus 1 elements from a finite group, we're guaranteed at least one representation for every element in A plus B. So this would imply that A plus B equals H, which just happens to be A plus B minus 1 by the pigeonhole bound. So that would be another way we can get equality. Oh, we've got a few so far. This very degenerate looking case, this robust case of arithmetic progressions that sort of comes from the torsion-free case. And here's one where it also looks a little degenerate. Just if the two sets are large enough, any two large enough subsets of H are going to sort of necessarily represent every element by that pigeonhole bound, and they just happen to have just enough cardinality to guarantee that equality holds. Now there's another example that might even be a little more out of left field. Let's say we have X inside H. Let's let H bar just be H minus X. So it'll be its complement. So relative to the subgroup H, we're just saying everything in H that's not inside X. And now suppose A and B are contained inside H, and the B equals negative A complement. Right, so it's just the complement of A. Let's look at the sum set A plus B. it's now sort of A minus a complement. So what's inside the set of, and let's assume that A is not periodic. We'll see why we need this after. So we're just assuming that we take a set A, the complement, we flip the signs and everything, we turn it around, and we're assuming our original set was aperiodic to begin with. So if 0 is an A minus a complement, that means 0 equals A minus a bar. For A and A bar not inside A. In fact, let's, what does this really mean? This means that 0 plus a complement intersect A is non-zero, right? Remember, these are all the elements of A that have can be used as a sum end in an element that represents 0. So we're just using that little fact over here. If 0 is in it, it has at least one representation. We'd have to have this being non-empty, but this is impossible. This is the complement of A. It's literally everything that's not in A. So this is impossible. That means 0 is not inside A minus a complement. What about something else? If X is an H, but it's not equal to 0, then the number of representations of X inside this sum set, A minus a bar, right, that's X plus A say X plus A complement intersect A. A is aperiodic. It's not a union of H cosets. So A complement is also not a union of any cosets or anything. So that means X plus A bar is not equal to A bar. Because if it was, it would be inside the stabilizer. And we're assuming the stabilizer is trivial. So that can't happen. So we have this set over here is not A complement. But A complement is exactly the subset that makes this empty. So if it's no longer A complement, it contains something inside this intersection. So it will have a non-trivial intersection. So that means X is inside A minus A complement. And we conclude this is everything in H minus 0. That's all we're missing is 0. We get every other element. We get 0. So its cardinality, that's H minus 1. That's A plus everything not inside A, which is H minus 1, A plus B. Again, we've got an equality. And this one, we start to worry a little because, I mean, the other two, this one here was, okay, it was trivial. This was a natural construction. This one, it was periodic. But now we got something that looks like strange behavior going on. We might start to worry that perhaps the sets that are critical can have all sorts of strange behavior that might be very hard to understand. We shouldn't get too pessimistic just so far. Because there's a better way to understand this final kind of set, where it's coming from. And if we sort of understand where it's coming from, then it's really not any different than the first relation. And so I want to talk a little about, well, how to sort of realize that the example 4 and 1 are really the same example. All right. So let's just consider our sets inside G, and we're going to assume it's finite for the moment. Then negative V plus AB complement is contained inside A complement. Why? Well, let's suppose this fails. Then negative B plus C bar has to equal A for some B inside B, A inside A, and C bar not inside A plus B. Right? Because we have an element here that's from B, something that's not inside A plus B. C is not inside A plus B. And if it's not, this equality fails, then it must be inside A, because it's the complement. If it's not inside the complement, it has to be in A. And this, of course, means that C bar, or that A plus B equals C bar not inside A plus B. That's impossible, because A is inside A, B is inside B. So this always holds. Now let's kind of look at this set over here. Because we want to understand when equality holds, and this is a subset equal here. Sometimes it holds with equality, sometimes it doesn't. What does this set on the left side really mean? So let's consider x in negative b plus a plus b complement. So x equals negative b plus c bar with b inside b and c bar not inside a plus b. All right, let's see when we add this to b. This should be contained inside a plus b complement. Why? If not, x plus b prime sorry, I want the opposite here. The element's not of this form. These are the elements that are going to satisfy this one. I had it reversed. If this is the case, if it's not in here, then we will get x plus b equaling c bar for some c bar inside the complement. And that, of course, means that x equals negative b plus c bar is inside negative b plus a plus b complement. Right, so these elements over here, the ones that aren't in negative b plus a plus b complement, when we add it to b, we don't gain any new elements. So let's just see what this means. If there's a gap here, if there's something that's not inside here, but it's inside a complement, in other words, if this equality fails, we could add that element to A, and it wouldn't change the sum set. would be nice. We could sort of saturate our set. We could just, if we want to keep on adding elements to our sets that doesn't change the sum set, we would increase the size of the summons. We sort of fill in the holes. And these are the elements that make this, the gap between here, the things that are inside the complement of A but aren't inside here are the ones that do that. So we might say that our set A is saturated inside the sum set if these elements don't exist. And by this little argument, that's equivalent to saying negative B plus A plus B complement equals A complement. Let's take a look at how the cardinalities reflect here. So let's suppose that A plus B is the sum of A plus B plus R. Just some constant. We just give a name to it that's how much more or less it is than the sum of the cardinalities. What happens to this sum set here? Negative B plus A plus B complement. All right, this is A complement, which is G minus A. And what is the sum of negative B complement plus A plus B complement? Sorry, negative B. That's B. Doesn't matter if we just change the signs, it has the same cardinality as B does. Plus G minus A plus B. So that looks like B plus G minus A minus B minus R. G minus A minus R. So this sum set, we put this together. All right, negative B plus A plus B complement. That's G minus A, which is negative B, A plus B complement plus R. Has that same difference. So what this means is if we start out with a critical pair which is saturated, satisfies this equality over here, we can't add any elements to A, we can't add any elements to B without increasing the size of the sum set. And we did this little strange complementation operation, we end up with another critical pair. It'd be another way to naturally construct critical pairs. And now let's do this in the case when well, I don't, it's a way to create a new critical pair. It's, in the end, we'll see there's actually like 3. So we have sort of A paired up with B. We can pair up B with the negative A plus B complement or negative A with negative A plus B complement. And so really a critical pair is part of a critical trio. There's this sort of third set, negative A plus B complement, that's always hidden in the background. And so I don't know if you want to call it an involution or not, but there's a third set that's always part of any critical trio. Let's suppose B is just a singleton element, right? Then A is saturated. All right, because if we add any element to A, we're going to increase the sum set. This is just a translative A, so we add another element to A, we still get something. All right, assuming A, there's something to add to it. If it was the entire group, there's nothing left to add. But as long as A is saturated, then this is going to be a saturated pair. So that means that by this little relation over here, no, I want to complement so well, we'll do it like this. B is also saturated. A is aperiodic. Right, because if we add anything else, let's just make this 0. If we add anything else to B, we would increase the size because A is periodic, so it has to go up by 1. Otherwise, we'd have, and then we get A minus A plus B complement is going to be basically 0 complement, which is H minus 0. In this case, G minus 0. And A plus B, this is just A complement over here. So this is exactly that type 4 pair. We're assuming our other set is not periodic. So if we add anything to 0 to it, we increase the size. That means it forces it to be saturated. And then by this general relation for any saturated pairs, we flip it around. The small singleton set becomes equal to saying the sum set has everything except one element, G minus 0. This is A minus A plus B complement. B is just 0. This is just A minus A complement. So as I was saying, that's why this sort of description of 4 is really just description 1 with this dual operation applied to it. So it looked different at first. It looked coming out of nowhere. But if you realize that you have this general relation in general, then it's really just that first type of a behavior happening again. All right, so these are 4 examples of ways we can obtain critical pairs. But there could be many more. So I next want to sort of describe a way you can take a critical pair, or maybe 2 critical pairs, and somehow combine them together to get more critical pairs. Sort of a process where you can add inputs and modify things and then get another new set which is critical afterwards. And to do this, we're going to need a little bit of notation. So let's consider H a finite group. A is a subset of G. And let's say we have this non-empty set, which we're just going to call A empty set inside A, induces a H quasi-periodic decomposition. I know it's a bit of a mouthful. What does this mean? A empty set has to be a subset of an H coset. And A minus this is H periodic. Right, that means it's a union of H cosets. So all we're really saying in the kind of this, when I was drawing these pictures, is that we could decompose A as everything that's not inside A empty set, unioning the A empty set. And this here is a union of H cosets, and this is a single partially filled H coset. lots of H cosets inside A. And there's one that may or may not be filled up. There's A naught. So this is nearly a periodic set. Nearly all the H coset slices inside A are full, contain all their elements, but there's one, this empty set where we don't know. It could contain everything, but could have some holes in it. It's just the one possible exception. And so it's nearly periodic, it's quasi-periodic with this quasi-period H. Now let's give a general setup as follows. Suppose H is a finite subgroup. A and B are subsets of G, are finite non-empty ones. Let's suppose A naught, empty set inside A, and B empty set inside B, induce H quasi-periodic decompositions. That just means that these sets are nearly H periodic. So apart from this H coset slice, in this case, H coset slice, A is just a union of H cosets. Let's also assume that this element, phi H of A empty set and phi H of B empty set, inside the sum set phi A plus B mod H. I mean, technically, these are sets, but there's only one element in it modulo H, because this is contained inside an H coset, so this is really one element. Is a unique expression element. All right, let's keep going. Let's suppose that the sum set is critical. And that the special slices are also critical. Right, so we have a bunch of assumptions, but here's our setup. We have our sets A and B. We have H quasi-periodic decomposition. So they're nearly periodic except for this exceptional two H coset slices. Now, that means this is a single element mod H, and B is a single element modulo H2. So this is a single element, live inside the sum set mod H. We're assuming that's a unique expression element. And we're also assuming that mod H, we have a critical pair, and inside that the H coset slices A empty set and B empty set, it's also critical. So here's the claim. That means A plus B is critical. This will give us a way to generate more critical pairs. We could just input a critical pair mod H with one coming from the subgroup H and combine them together to get a new critical pair in G, from one in H and one in G mod H. But let's verify this. So here's the short proof. Let's look at A plus B. This is equal to A plus B minus A empty set plus B empty set plus the cardinality A empty set plus B empty set. Why? Well, we're using is the unique, number 2. All right, we know this has a unique expression element, so this is, everything inside this H cosset is only obtainable by adding something in A empty set to B empty set. And here's the rest of everything over here. So particularly by 2 and 1, perhaps. Now let's look at this one over here. Since we have H quasi-periodic decompositions, apart from A empty set plus B empty set, everything else is something plus a full H coset inside A or B. So this is H periodic by 1. Because everything outside this H coset slice is just a periodic set. We just count how many H coset slices we have and multiply them all by H. So this is H times phi A plus B minus 1, all plus this. Right? We just have everything in A plus B mod H except this one H coset over here. But this is H times phi of A plus phi of B minus 1 minus 1. Because that's right over here. We're assuming the mod H, we have a critical pair. Right, so what does this look like? This looks like H times phi H of A minus 1 phi H of B minus 1 plus our special H coset slice, A naught plus B naught. Or H times phi of H A. This is just A minus A naught plus B minus B naught plus A naught plus B naught. Right, because again, we're just, we exclude that one special coset. This is just how many H cosets we have left in A, and it's H periodic, apart from that one little exceptional slice. So this is just how many other slices we have, which are all full inside A. That's the size of A minus A empty set. Same thing for B. And now we use finally the fact that we have a critical pair for 4. And together we're left with A plus B minus 1, as claimed. So it's a short calculation, but in the end, we can see that we can use these quasi-periodic decompositions. All we need is a quasi-periodic decomposition having a unique expression element. And we can use this and combine together something from H, it's critical, A empty set plus B empty set, with the mod H structure from G mod H that's critical, and get something that's critical inside G. So let's just say we had a critical pair mod H, G mod H, and it has a unique expression element. We have a critical pair inside H. let's look at this sum set A plus B. Mod H, A is going to be equal to X. Mod H, B is going to be equal to Y. We basically replace and just define automatically H quasi-periodic decomposition. So everywhere except for this special coset that corresponds to alpha and beta, we're going to in A have a full coset. And if we do this, we get a critical pair. All right, so we have over here special cosets. All right. Everywhere else, we've replaced it with a full coset. This set over here, if we replace each coset with a single element, looks like X. This one over here, if we reduce modulo A, looks like Y. And down here, we have basically copies of A naught and B naught that are translated. So this pair down here is critical too. So we can kind of blow up these two critical pairs. And we can construct lots of other critical pairs. So anytime we have two critical pairs, one mod H with a unique expression and one in H, we use these quasi-decompositions to create a new one inside G. And we could repeat this. We could iterate this over and over again to get like a sort of a layered critical pair. For instance, we could start with any one of those four critical pairs we had at the beginning. We could just combine them with these quasi-periodic liftings and get lots of examples more, lots and lots more. And they all be kind of recursively defined. Now this is starting to look like there's a lot of possibilities. There's some good news. That's it. That's Kemperman's theorem, that there are no other critical pairs, basically. I'll write that down formally, but we have those four examples from the beginning. We have a way of using those four examples and iterating them to get other ones. We could create lots of critical pairs that way. But all critical pairs are basically obtained by doing that. They're just recursively constructed, starting off with those four types and using these quasi-periodic decompositions afterwards. That's the essence of the Kemperman structure theorem. But let's actually write it down because it is a little bit of a little involved. So we're going to define elementary pairs. And our first option is that either A equals 1 or B equals 1. It's going to be our type 1 elementary pair. Our type 2 is A and B, our arithmetic progressions. Difference D with A plus B minus 1 being no more than the order D. Our type 3 ones are that A and B after translation are inside H. Now, and we're going to also assume there's a unique expression element because we didn't need actually periodic pairs for the general case, but if we want to do this quasi-periodic lifting, it's possible that even though we start off with an aperiodic pair, we could reduce down to a periodic pair. 4, that we have A equals negative B complement with A periodic. And this could be all relative to some, here, A and B are inside, say, H, or subgroup H, which is going to be part of this quasi-period. This is one way to define them. Let's just say these are the weak definitions. I could add some extra requirements over here. So I'm going to maybe change color chalk and add some conditions. Here to 4, I'm going to add there are no unique expression elements. And here to type 3, I'm going to add that there's exactly 1. It looks a little different. These are two different ways to define, say, these elementary pairs. And regardless of which one you use in the following theorem, it's both true. So let's write down Kemperman's theorem. There are more than one way to state this. I'm going to write down sometimes what's called the dual formulation. So A and B are inside G in a abelian group. They're finite and not empty. Yes? Let me write down Kemperman's structure theorem, and then I'll explain it afterwards. There's a reason, yeah. Let's come back to it. We can see the theorem where it's going to come into play. So then A plus B is equal to this critical bound, A plus B minus 1, and either A plus B is aperiodic, or it contains a unique expression element. If and only if the following all hold. So here's the setup. We're assuming it's critical and one of two additional things. Either they're aperiodic, and as we mentioned at the beginning, it would suffice to characterize all aperiodic critical pairs, because we could use Knaser's theorem to reduce the general case down to the aperiodic case. But we're also going to at the same time characterize those that are periodic and contain a unique expression element, because that's going to help in the recursion. And here's the possibility. Either AB is elementary of one of those types, 1 through 4. Right, so just one of those basic building blocks. Or there exists a finite subgroup, finite, proper and non-trivial, and subsets such that the following holds. And I'll write that all down over here. So 1, we have H-periodic decompositions. 2 mod H, we get a critical pair. Well, let's maybe first say this is a unique expression element. As I said, phi H of A and phi H of B is elementary. Of type 1 through 3. We don't need 4. That only happens if we start off with being, because 4 doesn't have a unique expression elements in the stronger point. Oh, and of course, we have criticality inside the coset slices. And inside A plus B, we have the hypothesis again that A empty set plus B empty set is aperiodic or contains a unique expression element. Okay. It's a bit of a mouthful, but this is exactly that quasi-periodic lifting we talked about, right? It's saying that we have an arbitrary critical pair with, one of these two things. It's either aperiodic or has a unique expression element. It either is one of those elementary pairs to begin with, or if not, it came from something else. Right? We had some quasi-periodic decomposition. Here are the non-empty sets, A empty set and B empty set that induce these H quasi-periodic decompositions. A empty set plus B empty set is a unique expression element. Mod H is not just an arbitrary critical pair, it's an elementary critical pair. One of these 3 possibilities there from the start. In the H coset slices, we also have criticality, and we have exactly what we need to iterate this theorem again and again and again. Right here, we then apply the theorem again to this one here. We can decompose this. It's either elementary of type 1 through, well, in this case, 3, and we repeat, and we repeat. And eventually we have to stop because the cardinalities are going down each time, and we have finite sets. And so it's basically, is what I said before, every critical pair is obtained by this recursive process. At each step, you're replacing, something with the mod H with the elementary pair, and then going down to the coset slice, and then examining that again. We zoom in to the coset slice and repeat, and repeat. Now the reason why these are in 2 colors is that we can define the elementary pairs either way. So it looks stronger if we have these extra restrictions here. But you don't need to have these restrictions, it's kind of optional. And it will change the recursion because what turns out is that if you don't have this restriction over here, it actually reduces down to one of these other pairs over here in the recursion. So if you have something of this form that has unique expression elements, it's going to correspond to one of these other critical pairs here or via some quasi-periodic construction with them. So it's really a matter of preference whether you want to have this extra information or not. If you have this extra information, you may need to iterate more times to get down these stronger restrictions. If you don't have these stronger restrictions, then you might not need to iterate quite as often, but you won't have quite as strong a structure there. You won't know anything about the unique expression elements, the extra bits for type 3 and 4. So it's a matter of preference which one you want to use, and it's maybe about a page or page and a half argument to show that it doesn't matter which one you use. How to get the subgroup? Well, it exists. It's just there. If you have an isoperimetric proof, then the subgroup H corresponds to a certain isoperimetrical defined quantity, so a hyperatom. But we don't really have time to get into that right now. So there is sort of a way to view where this H comes from in terms of this. I mentioned this briefly the other day, this isoperimetric machinery. That's where we don't just fix A and B as a single pair, but we sort of let A be fixed and we sort of let it range over all possible B's. We look at A plus everything that we add to it that's possibly critical. And then we can look at the behavior that happens there, and when you define things properly, maybe for a minimal choice of B that makes this true, it ends up being you get a coset at that point in a subgroup, and that one corresponds to the H from Kemperman's theorem in most cases. But that's a little more involved. But yes, yeah, so that's probably the only way I can give at least a partial answer to where that H comes from, apart from the fact that it simply is known to exist. Okay, we're nearly at an end here. It's a very useful theorem, and you shouldn't be intimidated by it. I know we spent the entire lecture just describing the statement of the theorem, and don't expect to really fully understand what the theorem says just in the first few minutes. I mean, I remember when I first saw Kemperman's theorem, I just studied the statement of it for a couple days before it sort of sank in. That's what was going on for me. And that was in Kemperman's original paper, where things were written. We didn't know quite as much at that point. But all that's really going on is that you have these four pairs and the recursive process, and that's it. And that's all this theorem here is saying. It's saying you take those four pairs, you iterate it. And there are two equivalent ways to formulate Knizzer's theorem. I gave this one over here, which, at least in practice, is now sort of seemed to be the more useful one more often. This is a formulation that sort of dates back to Lev. This is not how Kemperman originally formulated his theorem. It's an equivalent formulation, but it's not the formulation he used. You'll notice that here we more or less assume we have the elementary structure mod H, and we iterate by applying it to the coset slices. Now, there's, of course, a dual thing we could do. We could imagine, what if we knew what the structure was in the coset slices and didn't know what it was mod H, and then iterated and defined the structure mod H again? We go in the opposite direction. We know what the slices are, and now we have to iterate by applying it to the mod H structure. That was how Kemperman phrased his theorem. So he first zoomed in, and it's an equivalent statement. You have to be careful how you phrase it. You can also formulate it doing that way, and you'll just iterate it, and whether you start at the top and get to the bottom, or start at the bottom and get to the top with the iterations, you get to the same point either way. And so there are two sort of different ways to formulate it. It depends on where you want your structure. If you want the structure mod H, this way is more informative. It gives you sort of the global view of what's going on. Because this is just like a small set, and it often happens that this type 2 behavior for arithmetic progressions is somehow the canonical way. This is the only thing that can happen inside the torsion-free case. All these other pairs, either this is trivial, or they require some kind of finiteness to happen with subgroups. In the torsion-free case, that never happens. These two things don't happen here. All we have left are the arithmetic progressions. In the trivial case, one of the sets is size 1, because we can't complement without getting an infinite set. And if we go mod H, in some sense, we often either get an arithmetic progression or a very large sum set with respect to the cardinality of the group, right? When we have type 3, this is everything, right? So if we have a type 3 mod H, then we get everything except possibly for this one coset over here. So we have the entire group minus this one coset, plus whatever's inside this sum set of these two coset slices. At least one element, but it's everything except one coset. It's very big for the sum set. We have type 4. We get the entire group minus one element. Huge. We have type 1. Well, then we can't have really type 1 at the beginning, because then these are both contained inside an H coset. We just zoom down to H and repeat the process afterwards, right? Either that or this was just contained inside a single H coset. Right? A is inside an H coset, and B is just disjoint H cosets afterwards. That's a very degenerate case, but then we can sort of break it down, A plus each of the slices for B. It breaks down to simpler cases afterwards. And if you're wondering what happens when we don't have these assumptions, right, because this says A is aperiodic or unique expression element, we just apply this theorem mod the maximum period. All right, if it has a unique expression element, fine, we can use this, but maybe we don't know that. Then we're just going to apply this Kemperman structure theorem to phi of A plus phi of B. That's going to be aperiodic, so we can use the Kemperman structure theorem. And use that the number of holes, right, this A plus H minus A plus B plus H minus B is equal to H minus 1 by Kneser's theorem. Right, so remember that Kneser's theorem says we don't have too many holes. If it has exactly equality over here, we actually get equality in all those bounds. So we'd say the holes was exactly H minus 1 elements. And regardless of where we place those holes, because of that pigeonhole bound, we would still have something that had this sum set over here with this cardinality. Because we're guaranteed to have it being H periodic regardless of where we place these holes. So there's nothing to really be said about the location there. They're completely free as to where they can happen. And so we simply then apply mod H, get the structure modulo H, and realize that inside the non-mod H structure, there are some holes that are placed at random places, but there aren't too many of them. And that's how we have to deal with the case when it's periodic without a unique expression element. And I think that's enough for the day. So thank you.